Thanks, Randy, for the invitation. And hello, everyone. My name is Ying, and I'm a senior lecturer from University of Technology, Sydney. I would like to share some of my knowledge and thoughts in this specific field, which I refer to compare with the conventional assays, such as Western blotting or ELISA, those technologies that treat EVs as individual particles and get information from them individually. And here, broadly, I also refer to those digital format of assay, because technically speaking, the actual single EV analysis requires the technology to have the resolution to distinguish between single EVs and a group of EVs. So first, let's have a look at why we need to perform those single or digital EV analysis. Well, the first very obvious reason is, of course, because of their heterogeneity, originated from their different biogenesis, which can be then observed on their physical characteristics, either because of the different morphologies, even they are from single cell type, or there are different cargos, such as proteins and nucleic acids in different EV subpopulation. As mentioned by Professor Thierry this morning, if it's studied in a mixture, then a specific EV subtype that plays a key role as a biomarker signature or plays as a biological function may be masked by the presence of the other subpopulation. So that is why we need to carry out a single EV analysis so that we can extract the more accurate information from the specific EV subpopulation that we are interested in. The other reason, besides that, is due to the difficulty in separating EVs from the other extracellular particles. I think this has been talked about this morning in the EV isolation talk. And taking plasma-derived EV as an example, they are quite difficult to be separated from those lipoproteins, which share the same similar size and density with EVs, while have several orders of magnitude higher than the amount of actual EVs. While we could not get a 100% pure EV sample, the capability of the EV single EV analysis will allow us to differentiate the EVs from those other extracellular particles. And the third reason I want to share here is more related to using EVs as a liquid biopsy biomarker for early cancer detection. Recently, there are some new insights have shown that some specific EV subpopulation or specific markers in the surface of those EVs may have very low abundance. And this work is mainly from Professor Leiter from Harvard Medical School, who is a pioneer in the single EV analysis for the early detection of pancreatic cancer. And he proposed this new model showing that the EV actually carries very rare tumor-specific proteins. And here they compare the importance of this single EV analysis for early cancer detection, showing that with the single EV analysis, which can provide improved limit of detection, compared with the current imaging-based current standard, it is able to provide at least 2 years of monitoring window for those cancer patients. And here they also compare the limit of detection of single EV technology with the other more traditional method, which show that single EV analysis can detect low concentration of tumor-derived EVs in circulation, which is reflected to a small tumor volume in the early stage of cancer. Well, right now you may have the question, why can single or digital EV assays can improve the limit of detection? Well, let's take a step back at the fundamental analytical chemistry. The conventional analog-based assay is usually performed in a vial, such as a microtube or microplate. And the presence of the analyte will lead to the signal that can be detected. And this signal is proportional to the bulk sample concentration in the entire vial. While in the digital format assay, the sample is actually diluted and then partitioned into large amount of compartments that with a very small sample volume. And on this digital assay, each partition will contain only a discrete number of analyte, which can be then individually assayed, creating a result of either 1, indicating the presence of the analyte, or a 0, indicates the absence of the analyte. And this partition is actually the main reason that a digital assay can improve the limit of detection. This is mainly due to 2 reasons. First of all, in each partition, it has actually increased effective concentration compared with the bulk assay due to the significantly reduced sample volume. And secondly, the partition also allows a separation between the analyte and also the other interfering compounds, and thus increase the ratio between the analyte and the background in each partition, thus increase the signal-to-noise ratio. Besides the improved limit of detection, there are other advantages of digital format assay, such as they reduce the burden on the detection element. There is no need for the calibration curve like this because your quantification is only based on counting. And they can provide improved precision and linearity, also as well a wider dynamic range. Here I show some example of the commonly used single or digital EV technology, and I believe all of the examples shown here has been already commercially available. Most of them here shows using optical platform as a readout, while there are some exceptions such as the resistive pulse sensing, which is based on electrochemistry sensing. I'm not going to the detail of each technique. There are a variety of review papers based on this, and we are currently in the preparation of such review paper targeting on early cancer detection, so please watch this space. And then next I want to share what kind of the new information that we can obtain from this single or digital EV analysis, which cannot be achieved with a conventional assay. The first example is again from Professor Weisleider's group, which used a imaging-based single EV analysis to assess as many as 12 biomarkers from single EV analysis. And this multiplexing analysis is achieved through a multi-cycle fluorescence staining with a cleavable linkage. And the result showing from the single EV analysis that some commonly biomarkers that we use is actually has a less prevalency than we expected, such as this tetraspanins is showing absent in some of the single EVs that they analyzed. And here, this result is also asked us to be cautious with the EV isolation and processing protocols, because when we assess those very rare EV subpopulations, such as here, the example of KRAS mutated proteins, the sample preparation, such as here, the tetraspanin-based purification, may lead to some loss of this very precious EV subpopulation. And the next example I want to share here is from Professor Jovanovic Talisman's group, which used D-storm-based super-resolution microscopy to assess those single EVs. And here you can see that the super-resolution imaging can have a significant improvement on the resolution. And here this allows to analyze both the size and also the number of tetraspanins on each of the individual EVs. And from this data, they're able to identify a new population of EVs with a larger diameter and a higher tetraspanin contents. This allows to differentiate between pancreatic cancer and healthy controls. And this let us know with the capability of the new information that we obtained from single EV analysis, it may allow us to have new matrix with the diagnostic impact. As usual, I also share here some of my understanding of the gaps in knowledge in this field. First of all, there is a missing of the standard benchmarking method, and I believe that the role of cell search for the circulating tumor cells plays a good example here. Next, as I mentioned, I think in several talks, there is currently no universal EV biomarkers. Then the question relies on how we're going to quantify the total EVs. For example, the previous work from Professor Wisleider's group, they actually used a pan-EV reference that labels all the free amines in the sample. So that's actually have a high requirement of the purity of the samples that they analyze. And thirdly, most of the research that show in publication compare the analytical performance of single EV assay with conventional assay. However, in order to let them to be clinical useful, we actually need to assess their clinical performance, such as the sensitivity and specificity, compared with conventional assay. As many of the technique in single EV analysis requires EV labeling, so all the previous information from Charles talk about EV labeling actually applies here. And here I put some my own thoughts. If you're using technique that relies on immobilized EVs, then there is issue relies on there's no universal biomarker, and you probably will lose EVs during the staining and washing protocol. And those methods that requires the EVs to be suspended in the solution, then of course, washing of the unbounded dye, especially the antibody, will be a huge issue because EVs are quite small. On the horizon, it's exciting to see that many of the new analytical platforms in the market actually targeting on the single EV analysis. So I encourage everybody to talk to our sponsors and attending the sponsor sessions to get their insight. And also, it is exciting to see that in the field of development of the very frontier analytical technology, EVs are also used as a challenging and biological models for those developments. For example, here I show some studies such as a scalable optical trapping system and another infrared nanoscopy that can get the molecular fingerprints from single EVs. And this is the eye-scat microscopy, which is a label-free and highly sensitive method. And in this work, the authors using this technology to differentiate between EVs and lipoproteins based on their different refractive index. And as I mentioned in Laya's talk, machine learning, I think, is a very useful tool in the single EV analysis because single EV analysis will generate a large amount and complex data. Machine learning will help to provide a more accurate classification of the EV subpopulations. And the last is we are very excited to see that the new ICEV guideline is actually include those advanced approaches. So I extracted here also some related information to single EV analysis, such as you need to report the limit of detection, need to choose the most suitable EV reference materials. For example, for optical platform, liposome may be a better reference material compared with those more dense nanoparticles. And before you use the technology to more advanced application with complex sample, it's very necessary to validate those technology with well-characterized analytes and benchmarked with the standard technology. technology. And at last, we need to report the technical specific parameters to ensure a reliable and reproducible interpretation of data. And thank you very, very much for listening. Please feel free to contact me via email or follow me in X and visit my research website. And I'm looking forward to any questions in the panel discussion. Thank you.